Okay, so we were talking about preferential independence, which basically says that your preference order, whether you prefer more of the attribute or less of an attribute, does not change regardless of where the other attributes are fixed. Okay? So, and this is a very easy condition to satisfy. We see that people will typically not change their preference order, at least in reasonable ranges of negotiability for most attributes. One thing to distinguish this from statistical independence is that we understand for most decision problems that two attributes can be statistically dependent, and that's a pretty common thing that we see. So let's say we have reliability versus cost. Reliability usually comes with increased cost. Okay, so there's statistical dependence, but preferentially they're most likely independent, because regardless of where the cost is fixed, we prefer high reliability to less. Regardless of where the reliability is fixed, we prefer low cost to high. Okay, and that's essentially what it is. So that, of course, we want simultaneous improvement in both attributes. Nature does not allow that, right? So nature, it manifests itself in the statistical dependence between those two attributes, and reconciling the two is our trade-off behaviors with what nature allows is multi-attribute decision making. So, like I said, preferential independence is typically satisfied. There's some, we can always construct examples where it is not, and I leave you to think about those rare cases. Okay, so now we go to what's called utility independence, which basically says, in a nutshell, that for one attribute, let's say there's uncertainty associated with one of the attributes, right? We make the same decision under uncertainty corresponding to that attribute, regardless of where the other attributes are fixed, right? So utility independence extends the notion of preferential independence to the case where there's uncertainty present. Okay, so and utility independence implies preferential independence. So if you have utility independence, you can assume that preferential independence exists. But of course, the reverse is not true. Preferential independence does not imply utility independence. But these two conditions are necessary for us to be able to use the multilinear utility function. So utility independence applies preferential independence, allows us to use the multilinear form of the utility function. There's even more stricter condition, which is called the additive independence condition, which is even stricter. It implies utility independence, and in that case, we can use linear sum of single attribute utility functions, but it is very, very rarely satisfied. Okay, so there's three independence conditions: preferential, utility, and additive, in the order of difficulty to satisfy and how strict those conditions are. So I just wanted to spend some time talking about the additive utility function, which is, this is prevalent in industry quite a bit, where we would say, you know what, we have all these attributes, assign a weight to these attributes, add them together, and then you find the overall merit of a design or an alternative, and that is fraught with a lot of issues. Okay, you can only do this when additive independence is satisfied. It's almost never satisfied, and we see it's so prevalent that people will go through courses in multi-attribute decision making and still use this because they think it's easy to use, and just because it's easy to use does not mean that it's correct. And sometimes it's used even without utility functions. So people won't even go through these steps of assessing single attribute utility functions. They will just weight and rate the attributes, multiply them with scaling constants, and then weights, and then add them together, and that's the merit. I mean, just like off the bat, there's so many issues with it. One is that you have units issues. Different things are in different units. How do you get the right unit? Our preferences are non-linear. When we are at, let's say, a very high reliability, we may actually, per unit increase in reliability at that point, we may not be willing to pay that much money as when the reliability is low, right? But that assumes linear trade-off if you're just weighting and rating attributes. there's really no assessment of preferences under uncertainty. So there's a lot of things wrong with that approach, but it's used quite a bit. And one of the things that you can take away from this class is take formal decision analytic methods to your research or your place of employment, and then that way you'll make better decisions. Okay, so I'll just quickly go over the multilinear functional form. So the multilinear functional form looks like this. You have, let's say, attributes x1 through xn, and you have already assessed, based on the methods we've already talked about, you've already assessed the single attribute utility functions, ui, xi's, and if you use this expression on the right, you calculate the multi-attribute utility for an alternative with different values for different attributes. So, of course, we see the single attribute utility functions here. Here, we have scaling constants, which are ki's, the small letter k. They lie between 0 and 1, and there's 1 associated with each attribute. So after we're done assessing utility functions for each attribute, we also have to assess the single attribute, the scaling constants associated with single attributes. Finally, we have the normalizing parameter, capital K, which you can calculate using the scaling constants directly. So just a few properties. Why is it called multiplicative function? Some people even call it the multiplicative function, right? Because you see that they're multiplying this this expression over and over again. For each attribute you have k, ki, ui plus 1, and then you multiply those together. Why is it called the multilinear? Because if all attributes except the ith attribute are fixed, that is their constant, then you end up with something like this, right? And this actually is the thing that we should that makes the utility independence clear. You're making, if all attributes except the ith attribute were constant, then you're making decisions as if you're making decisions on the ith attribute, right? And the same risk attitudes and everything. So so the multilinear functional form becomes a linear function of the single attribute utility function of an attribute when all other attributes are fixed. Okay. When all the attributes are at the worst level, you get 0, as you expect. Okay. When all the attributes are at the best level, you get 1, as you expect. What happens when all the attributes are at the worst level except the ith attribute? Okay, so every attribute is at the worst level, so the utility becomes 0 in each case, except the ith attribute, which is at the best level. So here we put 1, and everywhere else we have 0. You can verify this yourself. This is pretty straightforward. If you look at the expression, guess what? You get ki's. So that hints at, oh, I can use it to assess ki's by saying that in the lottery, if the right-hand side had all best, all worst, and he had best in one and worst in the other, the probability p that you would give is the same as the scaling constant. Okay. So, and then when all the attributes are at the best level, you can use that to find k, right? So if you put all the attributes are at the best level, 1, 1, 1. Simplifying, you get a polynomial in k, because k1, k2, k3s are known, so you just get a polynomial in k, solve for it, and then you go from there. Okay, so pretty easy stuff. So we mostly limited ourselves to single attribute decisions. Numerous techniques exist to encode our preferences and make decisions involving multiple attributes. Some of them we discussed already. It's an active area of research. I still keep working in this area, and students are welcome to read further about multi-attribute decision making from textbooks and other resources. So at the end of the lectures, I'll go over a case study that integrates all these things. So I just want to give you a brief overview. So here's a work we did about 15 years ago now, where we actually solved a multi-attribute optimization problem. And guess what? Once we had the Pareto front, we applied the multilinear utility function to select the one with the highest utility. Okay, so we'll end this part of the lecture now. Okay, so let's get started now. Today we're going to transition to, so we're within these three modules here of optimization, uncertainty modeling, and then decision analysis. So we'll start with our brief discussion of design optimization. Of course, optimization, just like any of the topics covered here, are huge fields, and we can only cover basics. But today, in this short-ish lecture, we will just start motivating the viewers on why we do optimization, start with some notation and a motivating example, and then we'll call it a day for today, and then we'll start again with a little bit more detailed description of what optimization is and how it helps with system design. Okay, so basic and foremost thing, I don't think anybody will disagree that all product and system designs can be improved, right? So we always have an opportunity to improve on what we could do before we improve the characteristics. We can make things lighter, we can make things stronger, we can add storage to hard drives, we can improve the lift, we can increase the efficiency of jet engines, and we can reduce the or we can reduce the cost as we go. Okay, and the thing to understand is that most system designs traditionally were just ad hoc done, right? So we did simplistic analyses, we used expert opinions, we used best practices, and then we put together the system thinking that it would work the best. Okay, and often we would just be satisfied with that, but systems can be improved, and intuition only takes us so far, right? So if we allowed mathematical optimization techniques to improve the systems, then we have seen many times in practice that we can outdo intuition. Of course, that requires a mathematical representation of the systems. So and the benefits of mathematical optimization outweigh the efforts required. So the amount of time that you would spend in modeling the problem mathematically, the amount of time you would spend in writing the code or giving it to an optimizer in Excel or MATLAB is small compared to the efforts, the benefits that you can get out of it. Okay, and it's used pretty pervasively in many disciplines. So we have high efficiency systems, transportation systems, automobiles, aircraft now. We can maximize strengths in mechanical elements for the same amount of material used. Either we can come up with better designs, better dimensions. We can do in-depth analyses. Coupled with in-depth analysis, we can find better and better solutions that make our design stronger. We can increase profits in enterprises and much more. Okay, so so the objective here is to provide a gentle introduction to engineering design optimization as we used in systems engineering. All systems engineers should have a decent understanding of how to model an optimization problem, how to set up an optimization problem in commonly available software such as MATLAB or any other software that you might want to use, and then find solutions and then perform sensitivity analyses on the solutions found. Of course, that would also require us to be comfortable with the basic terminology and nomenclature used in mathematical optimization. Just like all disciplines, we try to use some standard language. We have standard setups for optimization problems. When you convey optimization problems to others, they will understand what you're talking about, what your objectives are, what your constraints are, and then you would also be able to use the software because most of them use standard terminology and notation. And you'll be able to set up and solve optimization problems, and then you'll be able to talk intelligently about optimization with peers and researchers. So that sometimes is important, right? Research and engineering practice does not happen in a vacuum. So if you're able to talk to your peers, you're able to explain the optimization problem you're trying to solve, or the problem you're trying to solve to somebody who's an expert in optimization, at least you'll be able to convey to them what it is that you're looking for. Okay, so there's many ways to think about optimization. The one that I like is optimization is search. Okay. Consider an individual searching for a wallet, okay, or their glasses, or phone, or car keys, or items in a grocery store. We've all done these searches, right? And we would think that, okay, well, a search is a search. How's this optimization? If you think back to what we discussed in decision analysis, when you are searching for something, you have an objective. You are trying to say, okay, I'm going to minimize cost. I'm going to find something fast. I'm going to do all those things. So there's many variables you're trying to minimize or maximize simultaneously when you are searching for something. Another intuition that you gain out of searching for things is that you start understanding oftentimes how optimization algorithms work. Okay, I can think of very few fields that color your thinking of the world and improve your understanding of engineering systems as much as optimization theory does. Okay, so when we're looking for a wallet, we would do an exhaustive search, right? But we can say, you know what, there's some preferred regions where I am likely to find it. Okay, so that's just to just add one thing here, that sometimes you could also be searching for unknown items, right? You don't know what it is that you're looking for, but you're trying to find. Or when you're buying a product, or you're looking at a new design, it's an unknown design. We don't know if we can reduce cost or improve reliability, improve lift in the wing or not. So it's still an optimization problem, but the end result is unknown. So the top examples that we have are known examples, and then we could also have unknown examples. So we have techniques that we use in real life. For, let's say, when you're searching for a wallet, you do exhaustive search. Okay, I'm trying to build a case for how to think about how optimization algorithms work. Right. So exhaustive search, you have to look everywhere it could possibly be. Of course, not everywhere you could possibly be, but places that you think it's likely, and then you expand the search area and expand the search area. But within the search area, you would do an exhaustive search. Glasses, you lose your glasses, you look for your glasses, same type of approach. But when you're looking for your phone, what would you do? What do people generally do?
Call the phone, GPS, find the location.
Okay, how does calling the phone help you find it?
If it is not in silent mode, then probably it will ring and let you know.
Give us an approximate
location.
Yeah, but how do you know the approximate location?
Via sound.
Sound, okay, sound. But we also have a way. Don't forget that. So when we do functional requirements or functional diagrams, remember we also have a sensor that can tell the intensity of the sound, the direction and intensity of the sound. Okay, so it's not enough that something emanates sound. We also need a sensor, which is our ears, to be able to tell that. So that's why I took this off. So either way, so you can call the phone. That gives you some sort of a gradient, right? That if you move towards it, the sound increases. Move away from it, the sound decreases, and then you can also use that to hone into where it is, right? And then in some ways you can think of optimization algorithms that rely on classical methods like the gradients and stuff. That's what they do, okay? And again, for car keys, you do an exhaustive search, right?
Modern car keys
Yeah, so modern car keys have location features too. Again, it's the same idea that that somehow you're able to use some information that it is providing. Now, if you're looking for an item in a grocery store, you can look for nearby items, right? So some heuristics work like that. You would say, okay, this is a good enough solution. If I tweak it, I might be able to get a better solution. So simulated annealing and genetic algorithms might work like that. You come up with a decent enough solution, look for it nearby. If things are alphabetized, I'm looking for something, and then I can see, oh, these things have been arranged in alphabetic order. I can then use that order to find something. So again, it's a gradient, right? Cost could be a constraint. Okay, you could say, I don't want to spend more than this. and then other attributes that may help narrow down a product, right? So again, we're trying to build intuition as to optimization is search. Sometimes there's things that we can use like gradients, and then we can also have heuristics, that things that are nearby may be a good predictor of what it looks like, what would the product I'm looking for, and things that, or the other thing could be that, if similar solutions exist nearby, almost saying the same thing twice, that then it may be there, right? So if I'm looking for laundry soap, I may go to the household section, right? That's a heuristic that we use. Every once in a while, stores will surprise you by putting something in an unrelated area, but the general idea is there, right? So all these techniques we use in real life. That's pretty much, you take that and you transpose that to the design space of a system and finding the best solution there. You're performing a search. Okay, so with that, so when we don't realize we're optimizing when we do real life searches, but we're optimizing when we're doing searches, but so we're trying to minimize time, effort, or money required. Engineering optimizations are a little bit more complicated, it goes without saying, right? And experience and best practices only take us so far. So one of the biggest challenges in using intuition or common sense or basic analysis in solving engineering problems is dimensionality, right? Often engineering problems involve dozens or hundreds of dimensions, and these are not spatial dimensions. These are different variables that you can control simultaneously. Okay, so when you have so many, so even for a simple, let's say, connecting rod, you can parameterize it many different ways and come up with many dimensions that you can change simultaneously. Plus, you can change the design or the material of it as well, slightly. So when your dimensionality is so large, then how do you do that using intuition? You cannot, right? So you rely on mathematical optimization, because mathematical techniques can systematically explore the design space and find you the best solution within those constraints, or at least find you a decent enough solution. So we may talk about convex and non-convex optimization problems. For convex optimization problems, a local minimum is a global minimum. For non-convex problems, many local minima exist. And indeed, for most engineering problems, many local minima exist, and that's okay. A local minima is still a good enough solution. We can start our search from many points and then find the best local minima we could find in our limited computational budget. The other reason intuition and common sense cannot be relied upon in making complex systems optimization decisions is limits in computational speed. There's only so much computation you can do. Computers can repeat the same process many times over. So even if you're not using a classical technique, you're using, let's say, a heuristic, genetic algorithms do function evaluation many times, right? It can do that because it's a computer. It doesn't get tired. So limits in computational speed that we humans have, and then dimensionality of most engineering problems makes it that you have to use software running optimization codes. Okay, so there's many examples that exist in real life where optimization helps beat best practices and intuition. Okay, so I mean, I could give you many examples from my experience. There was a friend of mine who had a model of an automatic transmission of a car. It was a fully validated model, and he was able to, and the way they were using it prior to him being part of that group was just to see how, what sort of efficiencies you get if a certain control algorithm is run. So, at this speed and this torque, you change to the second gear, and then you change to the third gear, and so on and so forth. So the model actually was able to implement that. He was able to change the shift points using an optimization algorithm and improve the efficiency by almost 20%, right? Because he used mathematical techniques. There's a common example that I quote in my class. So here's a paper that you can read. It's a very interesting class where they made a bent wire antenna, and here's just a schematic, like how bent wire antennas look like. and then they're able to look at the dimensions and the angles at each bend, and this antenna turns out to be very, very powerful for its size and energy requirements. So it's again something that genetic algorithms are able to find that we humans will struggle to find. And then if you look at the research articles, you'll see often that there's many examples of how mathematical optimization outdoes best practices and intuition. So just a brief overview of what optimization problems look like. There are three elements of an optimization problem: the objective or objectives. So you could do a single objective optimization. Connecting this with our decision analysis part of this course, that if you have the utility function and you're trying to maximize the utility function, you have converted all your attributes and the trade-offs into a single objective. Then you do a single objective optimization. You can not have that information, and you can simultaneously work with multiple attributes, and you already know what a Pareto front is, so you can find the Pareto front using multi-objective optimization, and then now you choose from that set of solutions which is non-dominated. So first element is objective, then you have decision or design variables, things that you control, your the dimensions, material choice, any decisions that you make, and so on and so forth. And then you have constraints. Okay, so all engineering problems have constraints. This thing should not exceed that thing. Stress should not exceed the strength. If you can have dimensional constraints, otherwise you'll get nonsensical answers. So all those constraints have to be put into the optimization model to get realistic solutions. One thing that we always say about optimization algorithms is that they are very good at exploiting modeling errors. So you have reality, which is your engineering system, and then you express that reality mathematically using a mathematical optimization problem. If you made any error in modeling, guess what? The optimization algorithm will take advantage of it. You say, okay, well, if I can make in an engine the piston diameter as big as possible, well, let's make it as big as possible, even if it doesn't fit in the cylinder, right? So you have to have that constraint that this diameter should be less than or equal to that diameter, and so on and so forth, right? So constraints, all these things have to be modeled correctly so that you get the answers that you desire. And sometimes you would have unbounded solutions. It'll say, oh, you know what? You can keep increasing profit if I just keep increasing that number. I can save you a lot of money if we didn't build the aircraft wing. So when you say cost optimization problem, if you don't have that constraint, then we'll say, okay, well, don't build it. So, anyway, so for a properly modeled problem, we'll say, okay, for an aircraft wing structure, if you reduce the cost beyond a certain point, you reduce material enough that it becomes weak. So that sometimes you can impose constraints that way. So objectives can be three types. More is better types attributes, like things that you want to maximize, like profit, happiness, fuel efficiency. Then you have nominal is better type attributes, right? So some nominal value is preferred. Size of a cell phone. Nobody wants a huge cell phone. Nobody wants a tiny cell phone these days. There's a nominal size and within which you try to stay. And then blood glucose level. Nobody wants really high blood glucose level. Nobody wants very low blood glucose level. Okay, so if you're designing an insulin pump, an automatic insulin pump, and you have a new idea for how to do that, you will have a target level. Maybe you'll have feedback, and obviously I think you need feedback. And then you say, we want to keep it near this nominal level. Okay. So, and then you have less is better type attributes or objectives, which are things that you want to minimize: cost, weight, deflection in a steel beam. So one of the first things we do is that we try to convert all optimization problems to minimization problems. Okay, same thing, like remember we had convention in how we draw Pareto fronts. Here's again we have convention. Of course, you can solve problems even if you didn't really follow these conventions. For example, if you start using Excel for optimization, it'll give you an option: do you want to maximize this attribute or minimize this attribute? That's okay, but make sure you stay consistent, okay, whatever you do. But it's always a good idea to follow convention so that you can communicate your optimization problems better. You won't have modeling and solution issues when you do that. So, and all these could be converted to minimization problems, right? So if you have a more is better type attribute, just use a negative sign. That's a common practice. When you have a nominal is better type attribute, you just measure the deviation from the nominal, right? You can come up with functions so that you can follow the convention. If you use lower is better type attribute, then you don't need to do anything, right? So that's just convention. Design variables are parameters that we control to optimize the objective function. These are basically your levers, right? You control things to, and then you see its effect on the objective, and you go from there, right? So, for example, your optimization code will tweak the design parameters a little bit, find gradients and Hessians, and then make the algorithms work using those when you're using classical optimization techniques. Examples are geometry of a part, choice of suppliers of X profit, and things like that, right? So, of course, you have to have a model for this. If you're using mathematical optimization, you have to have a model that takes your inputs to outputs, either through closed form expressions that you again write it in the code, or through a simulation model, right? So, if you do a change and then somebody has to run a CFD code, then you send those values to the CFD solver, and then it returns the value. If the code is too expensive to run, then you start doing meta models and things like that, and all that is sort of beyond the scope of this class, given the time that we have. But just getting you started in that journey. And constraints are things you can or cannot do in a design, right? So, for example, the cylinder should have a higher diameter than a piston. If EPA constraints, you might have something like, the amount of this chemical that you release in the atmosphere is below this ppm, or material compatibility. So you could say, I don't want these two dissimilar metals in contact. I don't want the strength of my whatever machine element that I have to be less than the stress it's going to encounter, right? So those kinds of things have to be there, or things like that. So, and these have to be models mathematically. You can't say that, okay, yeah, whatever, it'll happen. Somewhere the math should show that. Otherwise, as I said before, the optimization algorithm will take advantage of any modeling errors. So, I said earlier that optimization is search. So, one way to visually think about optimization problems is that it is a search of a good solution in a rough terrain. Okay, so think of your design variables as location in a XY plane, and the height of the function is the terrain, right? And your objective is, optimization is to find the lowest point of the curve or the terrain. So here we have a one-dimensional problem, but you could have two-dimensional, you could have many-dimensional problems. But many times these intuitions about how an optimizer is working helps us in understanding and extending our knowledge to a higher number of dimensions. Don't try this too much, but it's good to have some intuition about what's going on. Okay, so again, just to combine the three elements we talked about with search. So you say the things you can control to get the desired value of the objectives are the design variables. So let's say here I have only one design variable. We can move left and right. In our terrain example, so this is the terrain, or the cross section of the terrain. The location on the horizontal axis is the design variable, right? So wherever you choose is the design variable. And then we have some areas that are not allowed. So let's say you're not allowed to be here, so that's constraint. Right, and then the height is the objective function value. So just to give you some ideas of what's coming, these circles are what we call local optima. So we found locally the best point, right? So if you, from a classical optimization standpoint, your gradient of the objective function is 0 here, and your Hessian is positive definite, which means that the function is convex at this region. Okay, the function is convex at this region. Function is convex, so it's convex at all these regions, right? So it follows the local optimality criterion, but you can still get stuck in local optima. As you can see, this star is much lower, much better, because we minimize objectives than the other points, but you may not always find it. So you can get stuck here, and then your optimizer stops, and that's commonly observed, is perfectly okay. You start at a different point, and maybe you'll get stuck here. If you started at this point, maybe you'll find the solution at that point. So most optimization problems are non-convex, as this is, and you can only guarantee, optimization algorithms can only guarantee local optimum in those cases. Okay, but even those local optima are much better than what you can come up with intuition or just by guesswork. Okay, so like I said, many optima exist. Circles show local optima, stars shows global optimum, and then at least in this domain, no other better solution exists. Okay, so just trying to extend that into 2 dimensions. Of course, you have x1 and x2, 2 design variables, and the objective function lives in the 3rd dimension, perpendicular to the screen here, and you can see that now we show constraints at these curves, and we have infeasible regions. Okay. So you have two design variables here, x1 and x2. We have 2 constraints that we show here. These are non-linear constraints, as you see that they don't look like a straight line. We have infeasible region. So here constraint 1 is not satisfied, constraint 2 is not satisfied, and here both constraints are not satisfied. So of course your feasible region is this area here. And objective improves this way because since I cannot show the 3rd dimension, objective lives perpendicular to the screen, you generally have an idea of, okay, well, if I move generally in this direction, my objective will improve, means that my objective function will reduce in value. Sometimes we show it using level sets. And if we keep moving here, we hit a constraint. We cannot move any further, so we found a solution, right? So just some basic concepts. The dimensionality of the solution space is equal to the number of design variables, right? So these are not spatial dimensions. It could be the current, it could be physical dimension, it could be let's say capacitance, so basically you have many variables, and they define a design space which has dimensionality equal to the number of design variables. And these are not spatial dimensions. So spatial representation, all these pictures that I've shown you so far help in visualization, but since you cannot plot more than a few dimensions and you cannot really imagine them, we should only use them as a way to improve our understanding, but they won't give you a complete understanding of what's going on. So I'll just have a couple of things that we'll talk about today. One is the standard formulation of an optimization problem. So we have the objective, usually written as f of x, which is minimized. And the objective function is a function of the design variables x, which is a vector. And it has different elements. They could have nothing to do with each other, or they could have a lot to do with each other. Some could be dimensions, some could be material, some could be discrete, some could be continuous, and so on and so forth. And you have equality constraints. H of x equals 0. So h is again a vector. So you could have many equality constraints, right? So we could say that the diameter of the piston should equal the diameter of the cylinder, right? If two parts have to fit. We could say that something should equal something else, and so on and so forth. And inequality constraints basically guarantee that some function of the design variables is less than 0, right? So even if you have, let's say, for h of x, you could have a quantity or a function of the design variables equals some other function of the design variables, you can still convert into standard form by transposing. And similarly for inequality constraints. So this is the standard formulation or the elements that go into the standard formulation of an optimization problem. And we would write an optimization problem in this fashion. We would say minimize f of x using x as the design variable such that h of x equals 0 and g of x is less than or equal to 0. Again, x is a vector, H is a vector and G is a vector, which means that there could be multiple equality constraints, multiple inequality constraints. And often we could say that, this all these constraints together define a set X, which is the feasible set. So we can just write this as minimize such that X is the vector, the design variable is is an element of this feasible set, capital X. And that's also gives us intuition sometimes if we are interested in the properties of that feasible set, right? So in optimization, we like convex optimization problems, right? So we need to define the properties or understand the properties of the feasible set. If so, we say, okay, well, let's look at what the feasible set looks like, and if it's convex, then our day is made, and so on and so forth, right? So sometimes we're interested in the properties of this feasible set. Okay, so takeaways for today, and we'll keep this brief, is that optimization is search for the best solution. Designs can always be improved, and mathematical optimization easily outperforms intuition and experience. Okay, and we should follow conventions when writing down optimization problems as much as possible. So the next thing and the final thing we'll do today is this problem that I consider a very interesting, motivating example that I give to students. So let's say I have 4 cities at the corners of the square. How can we minimize the length of the roads built connecting the 4 cities that are located as shown below? Okay, so the objective is to build roads such that you can get from any city to any other city by minimizing the length of roads you build. Okay, and of course this is there could be, I mean, you can complicate this problem by adding many layers, but even in the simplest form, you can think of it like this, that if, let's say, the cities were, or the size of this square was 200 miles, then you could easily be saving tens of millions of dollars with an optimal design. Okay, so this is again some place where intuition should not be used, right? So what do you think is the solution?
By creating a junction at the center.
Okay, so one solution that I'm getting is that we connect these two using two diagonal lines, right? But let's work through it systematically and not jump to that conclusion. Okay. So first is this. I can connect using straight lines. Okay. The length of total roads we'll build is 8a. Okay. So okay, just keep that away. In fact, if this was being solved using a genetic algorithms, this is sort of how we'll approach it. You'll find a solution, find another solution, compare it in the selection stage, excuse me, and select the better solution, so on and so forth. Then you say, what about this solution? You say, oh, hang on a second, that's better. I can still get from one city to another city, but as opposed to 8a, now I take 6a length of roads. Okay. I can also do this, right? This is also 6a. So this line can be moved up and down and you'll still get 6a. The thing to understand here is that we are intentionally simplifying this problem. We could add all sorts of constraints. Let's say, what if there's a lake here and some other mountain range that you couldn't go through? So all those things necessitate using an optimization algorithm, but for now we're just using common sense, right? So then what you do is that you say, try this one, okay? And then you say, okay, that sounds promising. That might actually reduce the length of the road to the smallest, but what do we not do in optimization? We don't trust our intuition, okay? We let the optimizer find it, okay? And we can always verify if it finds a solution that we also thought was correct, then that's great. But maybe you'll find a better solution, okay? So we'll return to this problem in the next class, and yeah, and then I think that I want to end today this lecture. Okay.